We're now going to begin a set of tutorials to learn how to create a surface forcing field that we use to force the ocean model, the ROMS model. Now I'm logged in on the Xios here, and I'm going to go in ROMS NC files. And first I'm going to clean all the netcdf files that I've created in my previous examples. And so in this directory you'll find a whole bunch of scripts that begin with main underscore something. I'm going to begin focusing on the first script that is for the forcing file, which is called main underscore nc files underscore fork. So let's open this. And the idea here is, this was created some time ago now. And the logic here is that first we create an empty recipient forcing files for the grid that we're working with. And keep in mind that you can create also, forcing file for each of the forcing variables. This is just that ROMS allows you to do that. But for this particular case, we're going to start creating a seasonal forcing file, meaning a 12 months climatological forcing, and we're going to store all the variables in one file. The second step is to set the times in the forcing file for each time variable. In other words, if we are doing monthly mean climatology, we're going to set the time to be, say, the 15th of every month, and that's going to be our average date. The third step is to extract the actual forcing field from some of the available data sets, like, for example, for this example is going to be the ANSEP reanalysis. And then the last step is to interpolate the extracted fields onto the model grid and then save it into the netcdf files. Now by default, this program, this script, will extract these particular forcing variables that are listed here. And it's SH flux is the net surface heat flux. SWRAD is the solar shortwave radiation, which is often used to, for example, for the vertical mixing schemes. SW flux is the freshwater flux, in other words, is a surface boundary condition for salinity. SUSTR and SVSTR are the momentum stresses in the U and V direction. And then SST and SSS are the surface temperature and surface salinity, which may be used sometimes in conjunction with a relaxation condition, for example. And the QDSST is also used in conjunction with a relaxation condition for the sea surface temperature, and it's basically the derivative of how dq changes with SST. In other words, how to adjust the surface Q heat flux. Q is the net surface heat flux in response of a change in sea surface temperature. So if you wanted to use this script, all you need to do here is to just put here the name of the grid that you want to use, the output directory where you want to store things, and then that's select whether you want a time-dependent or climatological forcing. In this particular case, we want a climatological forcing, and so we're going to place this to 0. And at this point, all you need to do is you go in MATLAB, you go in this directory where I have these scripts here, you fire up MATLAB, you do an ls, and then you just execute the script. And you wait. And you can see this is now doing the seasonal climatology. It's pretty fast, and it's doing all this stuff here. Now it's doing the surface fresh and heat fluxes. And while we wait until this is finished, now let's go back to this thing and let's look in detail what exactly is doing for the climatological forcing. Yeah, it's still going. So the idea here is that you have these steps. The first step is to define the times and create a forcing file. And these are details that you don't necessarily need to know if you just use the script as is, but since you're going to be customizing things, it is important to understand more or less what's going on. So here in the first part, fork file is the name of the forcing file. And then there's this option array. And this option array is used to create a new forcing file with the specific conditions. In particular, SMS time is the time array for the surface momentum stresses. And here by setting it to 12, I'm saying that there's going to be 12 records of it. Then I'm going to have SMS time cycle underscore cycle, and I'm going to set this to 360. In other words, I'm saying here that this forcing is periodic, and it's periodic within 360 days. And that's how I define the periodicity of the forcing, so that if you run the model for more than, say, a year, the model is going to automatically restart forcing the surface with the same forcing after 12 months and so forth. The last thing here is SMS underscore time val, and this is basically the actual time values of the forcing in days. And so here I have an array of 12 records that goes from day 15 and with an increment of 30 days up to day 360. So it's basically the midday of every month. So it's 15, 45, and so forth. Now this is done for the SMS time, which is the time variable for the surface momentum stresses, SMS. And the same needs to be done for each of the forcing variables. So I have one for SHF, which is the surface heat fluxes, and this is underscore time. And so again, I have a cycle and the actual values. And because this is a climatology, all these variables are about the same. So once I have that, then I can create a forcing file by just using this function and giving as input argument the GRD, which is the grid, where it takes all the parameters, the name of the forcing file, which was defined up here, and then this option array, which is defined here, which has all these definitions so that it's just already configured the file for you. So this will create the empty file. The second step is to actually extract the product of choice, in this case the NSEP reanalysis. And the way I do this is first I create a CTL, a control array for the forcing file. I just do RNT CTL, the fork file, and the name of the time variable. In this case I use SMS time, and since the time variables is the same everywhere, it doesn't really matter. Then I write down here the variables that I want to extract from the NSEP reanalysis, and in this case I want to extract basically the surface heat flux, the surface the solar radiation, the surface freshwater flux, SUSCR and SVSCR, and then I just run extract surface forcing file, and all it needs to know is the longitude and latitude of the grid, the date, and in this case it's in the MATLAB convention datenum, and in this case 1530-360. Then I say clima here to indicate that this is a monthly climatology, and then I said just put the name of the variables and so forth. Then I go on and I extract, and then I assign this to this fork D array. Then I go on and extract the sea surface temperatures and sea surface salinity from a different data set, which is the Levitus TNS clima. Once again, I have longitude, latitude, the dates, and then the fact that I only want to extract the surface. And then the last thing I do is I have to get this flux correction, dq/dSST, okay, term. And there's a function here that's called RNC extract dq/dSST clima. Again, longitude, latitude, and time. And so then I have these fork D, fork D2, fork D3 arrays that contain these extracted forcing. And if we go back in MATLAB, now you see here it's actually finished creating the forcing file. If I do ls minus RTLA, you find that your forcing file is right here. Okay, so I can NC dump that, F12, more, and you can see that it has all these variables inside, and it's populated with stuff. So actually this is already done. But if I look at these fork D arrays that I extracted, you see this is the one for the SUSCR, SVSCR, and then these are all like three-dimensional, two-dimensional arrays that are used for the computation of the surface heat fluxes. And so then here I have the SVRAD and so forth. So once these are created, and I have one for fork D2, this is done. This is for the SST and SSS, and then I have fork D3, which contains the dq/dSST and so forth. Once I have those, then the last step that this script does, it just uses this function called RNC interp to grid NSEP to basically interpolate these fields into the model grid and save them into the netcdf file. So this really has CTLF, which is the basically it's the control array that points to the forcing file. Fork D in this case is this extracted forcing, and GRD is the grid. And so depending on whatever is in fork D is going to be put into the file CTLF here. Okay, so you can use any. So in this case we call this 3 times because we have fork D, then fork D2 for the sea surface temperature and salinity, and fork D3 for the dq/dSST term, which is used for the surface correction. So with this is all it does, and the next section is going to be on a time dependent. But as you can see, you can just modify here some of the parameters if you want to, and then just execute the script. Okay, so this is all for this seasonal forcing. And once again, the CTLF here is actually loaded, so I can always load, for example, a particular variable here. grid RT load var, for example, if I want to, of a CTLF. Let's load the January, for example, and then I can load this SUSTR here. And I can make a plot of that RT PLCM of SUSTR, comma, GRD. And what I see here is I basically see you know, that at these latitudes I have in the seasonal cycle, I have the winds that are directed towards the east. Where they're closer to the equators, I have the trade winds directed towards the west and negative. So this is positive U and negative U, so which is typical of the northern hemisphere oceanic basin, or in general northern hemisphere atmospheric circulation. So, and you can check all the other variables if you want, but for example, you can check the sea surface salinity, for example, and this would be SSS, and so let's load it, SSS, and then we can plot it. And here what you find is that you have a fresher salinity in the higher latitudes where it rains more, and here you have you know, saltier salinity, and that's because you have more evaporation, okay, on average. So this is consistent, and so now you have a forcing file that you can either plot or use to force your ROM simulation for a seasonal cycle simulation. Okay, this is all for this tutorial.